Yes, thanks, Blaise, and thanks the organizer all to give me the opportunity to talk. Unfortunately, I cannot be there. I'm sorry, but for personal reason, it was not possible this time. So the talk of today is based on a paper I did a couple of years ago, and we talk about active matter. So since I think not many of you are familiar with the topic, I prepared just a very basic presentation, and I think we should start from the dictionary, which is most of the time the most difficult part of the story. So what is active matter? Active matter is an assembly of interactive particles which are active, so they self-propel themselves and they collectively generate motion or mechanical stresses. So the drive, so the active force is not something that you can think about in standard non-equilibrium system where you put just an external force or a different boundary condition that drives you out of equilibrium, but the non-equilibrium part of the problem comes from the particle itself, which are active and propel themselves, okay? So there are many examples, mostly from the living world, but not only from the living world, which runs from schools of fish, flocks of birds, bacteria, and so on and so forth. I will speak about some of them in what's come. What is an active particle again? Probably one of the most known example, the first probably example of active particle are bacteria, and probably the best known example is the Escherichia coli. Active particle is a particle that transform chemical energy into motion or mechanical forces through some internal secret transformation. So, for example, the Escherichia coli uses his own energy to propel himself with the tail, moving the tail. Okay. So, what's the peculiar property of these particles? For example, in bacteria, a single bacterium lives in this what is called the low Reynolds number propagation. What does that mean? It means that at this case the viscosity is it wins against inertia. So as soon as the bacteria stops to self-propel itself, basically stops to move after very almost instantaneously. So people think about the motion of a single bacterium as a low Reynolds number propagation, and that tell us that these systems are intrinsically at non-equilibrium. So by the time the activity, so the cell propulsion of a bacterium is not there anymore, they stops almost instantaneously to move. On the other hand, that's the first lesson we learn. The second one is that these activities also generates collective emergent behavior, which are not common to standard equilibrium system. So, for example, if you consider not only a single bacterium but many bacteria, they do generate collective behavior with many emergent properties like vortices or even turbulence. So the activity itself generates also phenomena which are emergent and different from standard equilibrium system. Where do this system appear? Of course, I told you I made the example of bacteria, but the active matter are ubiquitous in nature. They start from a school of fish, from birds. There are also non-living particles that are active in some sense. For example, nanoparticle propelled by catalytic self-generated forces or layers of vibrating granular rods. So there are many systems that can be considered as active and that can generate collective behavior which are not common to standard equilibrium system. Okay. So what do these systems have in common? So basically, as you can see, the properties of this system, so the system are many and variegate. People in the past started to think about what do these systems have in common. Basically, there are some properties that you can extract and that are common to all these systems. For example, the fact that the activity, so the drive, acts on each unit and is not applied through boundary condition, as I told you before. Also, typically active particles are elongated. So if you think about a fish or a bird, you can distinguish the head from the tail. So they do have a shape, which makes them a characteristic shape. So they typically present some orientational order. So you can distinguish the head from the tail and so on and so forth. Even in Escherichia coli, this is the case. So they form what is called living liquid crystals. Um, and on top of that, there is this fact that they do present emergent phenomena which are out of equilibrium. Okay, so people started to see, are there some underlying universal properties? All these features are common to all the system you can think about in active matter. People started to think if there are some underlying universal properties of this system. And what one can find is that first, the emergent behavior that you find once you consider collective system is qualitatively different from the individual constituents, and this is the case, for example, for the Escherichia coli. Um, the patterns formation are on various scales. For example, you have always a long range fluctuation in your system. The rheological property is typically unusual. So, for example, a cell stiffen when stressed and adapt to their mechanical properties, or for example, the bacteria can deform its shape when it has more bacteria around himself. So the in essence, the description of this system is inherently difficult, and mostly because they are out of equilibrium, and because the interaction, if you want to model this interaction in an effective way, it's hard to define what to choose as a main interaction. Okay, so people started to do some schematic assumption how to model interactions, and the main kind of interaction that you can find in this material are two types. The one that we call polar, which is the dominant one in fish, birds, or bacteria, where you can distinguish the head from the tail. And in our talk, we will mostly focus on the polar system, as the title says. Or there is also the kind of system in which the interaction are apolar, so you cannot distinguish the tail from the head. For example, this is the case in active rods and something like a system like that. Okay, and depending on the nature of the system, if it's polar or apolar, you can also have two types of orientational order. So there is the polar one, where the moving states align all the velocities into one direction. If you want a simple example, you can think about a flocking of birds. First, the birds move randomly, so the average velocity is zero, and then at some point something happens, the flock is formed, and they all fly together with a constant velocity in the same direction. So this is a sort of a polar moving state. There is also what is called apolar or nematic orientational order. Also, polar active matter can have this kind of order, but we won't focus on this. And for sure, this is the only case possible for apolar active matter. Okay. There are also two types of interaction. There is one which is the one we're going to consider mostly, which is the Vixek one, in which you have a sort of nearest neighbor force which tends to align the velocities of the bacteria or your system in general. Or there is another kind of interaction which is mostly like an hardcore interaction, in which because of a shape, when the two particles come very close, they are forced to align in a certain direction. This is something very common in active rods, for example. Okay. So again, if you want, given that we have classified the possible kinds of active matter and possible kind of interaction in those categories, now our aim is to model this system. And we need to extract the basic properties that any system of active matter, of polar active matter, have to present. So the first one that we always have, we've seen before with Escherichia coli, is that the flockers, the boids, are always moving. In the sense, as I told you, that the activity makes the system out of equilibrium. So one consider that the boids cannot stop. Okay. Um, on top of that, the boys tend to align their direction of motion. So if they are close enough, there's some interaction between boys that and they tend to align their orientation. And this is the prototypical example. In this case, is the flocking of birds, if you think about it. Okay. On top of that, since the boys are most of the time living particles, they can make mistakes. So you must add some noise to the system in order to parameterize the fact that the alignment of the velocity is not always exact. Okay. So probably the very first effective example of a model that describes active polar particle was derived in 1995 by Vixek. And this is a sort of in essence is similar to what you do in the Ising model, but in contrary to the Ising model, in this case the particles are moving, and you update at each time step the position of the boids by just the standard velocity rule. Okay. The velocity of each boid is at each time constant, so the modulus is just equal to v, and the angle, so the direction of the velocity depends on an alignment force which depends on the nearest neighbor. So at each step you find the nearest neighbor within a certain radius r. And you tend to align the velocity to the average velocity of the neighbors. And there is a delta, what I call delta theta, which is a random noise. So the alignment for the nearest neighbors is not exact, but you can have some random Gaussian noise which tends to disalign the boids. Okay, so this was the very first basic example of to model a polar active matter. And if you do that, what you find here is some schematic order, mostly into dimension. As you see, when if you are at low noise or at low density, the boids tend to align their velocity. If you increase the noise or lower the density, the velocity distribution is just random. Okay, and so the order parameter of your system is indeed the modulus of average velocity of the birds. So the first time Vix model appeared, it was mostly a two-dimensional model. That's because they were interested mostly in bacteria, so the bacteria moves basically on surfaces. So they were interested in applying describing system which lives in 2D. And in 2D, you have some theorem from quantum field theory and statistical mechanics, which is the Mermin-Wagner theorem, which states that a continuous symmetry cannot be spontaneously broken at finite temperature in system with sufficiently short range interaction in dimension lower than or equal than 2. So basically, this is a very basic theorem in statistical mechanics, and people start to think about what was the assumption that was broken in the Vixek model that makes it possible for this spontaneous breaking of symmetry to happen. Okay.
Sorry, one question.
Yes.
But is this a phase transition or a crossover? How are you so sure?
It's a phase transition. I think you before you are breaking rotation invariance in some sense. No, you have at some point you have a velocity which points towards one preferred direction, and before you don't have any.
Okay. 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 Yeah, go on.
Okay, so people start to think, what is the Benjamin-Wagner theorem violated? Actually, there was a long time passed before someone brought a solution to that, and in that sense, hydrodynamics comes to the rescue. So let me just tell you basically what a hydrodynamic is. Hydrodynamic is an effective constraint continuum theory that describes the long time, long distance, or small frequency and wave number dynamics of most interacting many-body system. Okay, so what you do to write your relevant hydrodynamic equation, you basically first derive what are the symmetries and conservation laws of your system. For example, in the case of a standard fluid, the relevant variables are the velocity and the density of the density fields. Then you decide what symmetries you must retain. For example, in the standard fluid, you have rotational invariance, space and time translation, and Galilean invariance. And you set the conservation law. So you want the conservation of particle numbers and momentum energy in a standard fluid. How you retain the relevant terms in your equation? Then, well, since you are describing a coarse-grained system, so it's a small frequency, small wave number description, you perform a derivative expansion. So you retain at first terms which with the lower possible derivative. So if you do that with a standard Galilean invariant fluid that we are used, you arrive to the Navier-Stokes equation, which are this one. Now, um, why I say hydrodynamics comes to the rescue in the case of active matter, because one year later, Toner and Tu explained the activity of a system in terms of a certain effective hydrodynamic description. So what they said that in a VU system like the VXEC1, the relevant variables to describe the moving are again the velocity and the density fields. Indeed, you still want your density to be conserved because the total number of voids is a constant of motion. On the contrary, the symmetries are not the same as the standard fluid, but you still have rotational invariance in the disordered phase. You still have space and time translation, but since the velocity of the body is fixed to be one, the modulus of velocity is fixed to be one, you don't have any more Galilean invariance. Okay. So on top of that, since because of that, for your conservation equation, you have a conservation of particle number, but you might not want to conserve any more momentum and energy because the system is active. So they retained this assumption, and they came out with an effective Navier-Stokes equation in which you have more terms than the standard one because you have less symmetry. For example, this lambda one was not fixed. You have a noise part eta because you want again to mimic this noise, the fact that boys make mistakes, and you have. What mimics your activity, so what makes the velocity to be aligned, which they mimic as a sort of Mexican act potential, which is this point to potential here that I put in this equation. Okay, so if you want, okay. And on top of that, the flux are compressible, so the density is conserved overall but can fluctuate. So they have an equation for the density which is of this kind, with a pressure that can depend explicitly on the density.
Can I ask a question?
Yes,
On that previous slide,
yes.
yeah, so how should I understand that this term, which you say aligns the birds with the boys with the neighbors? How does it do that? Because it
Well,
like it's fixing. It wants to fix the modulus of the velocity to something, but I
yes,
don't
exactly.
understand. I mean, at this point, you're just talking about a collective velocity variable, and I don't see how that serves to distinguish what the individual components of the system are going to do.
Well, okay, let me explain this in that slide. So, okay, as you say, you have first you have a complete rotational symmetry. Then you fix the modulus of velocity, like in your Mexican act example. Okay, so you have that the velocity is fixed to some value, and then you have to pick. So if the vacuum sits into a specific angle, so at equilibrium, all the birds are moving towards a certain direction. Of course, this is one of the possible vacua. So the vacuum is continuous, and they are connected by something that you typically call a Goldstone boson. Okay, so this is what they wanted to do in some way. The orthogonal fluctuations, so the fluctuation orthogonal to the modulus of this velocity, which is alpha over beta, are what you typically call in statistical physics the Goldstone boson, and connects one vacuum to another. Okay, and indeed, what they do is say, okay, you have some sort of spontaneous breaking, symmetry breaking, because you choose a modulus, then the fluctuation along the velocity direction becomes massive because of the potential u, and the fluctuation orthogonal to this potential are what you call the slow mode, so your Goldstone boson. Now, of course, if you want to have you really want to check if this VPERP is really a slow mode. So if the fluctuation are not destroyed like in the standard Mermin-Wagner theorem. Okay. So one can basically tends to do a linear analysis at first. So you just perturb your system around your equilibrium configuration. You know that v parallel is massive, so you integrate it out, and you are left only with the perpendicular fluctuation of the velocity, and you just discard all the terms which are non-linear in the velocity, like the blue one in my slide. If you go to Fourier space, you can actually solve exactly for this fluctuation at the linear level. And you can eventually compute the correlation function, assuming that your noise is just Gaussian, so that the average is just the usual delta function. Okay. So what you end up with is that if you do that and you compute the correlation function, you still have the logarithmic divergence that you find in typical 2D systems. So the Mermin-Wagner theorem at the linear level would tell you that there's no order in this system. Okay. That was the linear analysis. Still, the nonlinear term, Toner and two, actually noted that the nonlinear term invalidates the Gaussian infrared limit. So basically, if you do just a scaling analysis, like an RG scaling analysis at the linear level, you find that you have an anisotropy because you have different scaling in the longitudinal and perpendicular velocity direction of the velocity. And if you compute the scaling of this advective term lambda 1, one can easily see that it is becoming relevant in d less than 4, and in particular is for sure relevant in d equal to. So what they did was to do again the normalization group analysis just using this fact, so including this relevant term in their analysis. And what they proved is that the velocity fluctuation goes like L to the 2 chi. Chi is one of the critical exponent of your Toner 2 equation, and that typically this chi is a negative number. So basically, in the advective terms, the nonlinearities are driving the system away from the standard Gaussian fixed point, and what you find is that in this case the order is preserved. So basically, it's a sort of the activity. So the fact that your Mexican net is choosing a preferred non-zero velocity state together with a nonlinearities is fixing is driving you is sort of violating the Bernoulli-Wagner theorem. Okay. So that was the whole story. Now, what here start my small contribution to this story, and the fact the main problem is that the Turner two equation are most of all effective. So all these additional term coupling constant that you add were not fixed, and they were treated as phenomenological. Okay. Uh, so I started to ask myself, since I was where I am working on from hydrodynamics, if these Turner two coefficients are really arbitrary. Okay. Um, Now, where is, as I told you before, where these phenomena, the three domains in Tonnerre 2, they write this phenomenological equation, all these lambda 1, lambda 2, lambda 3, the potential U and the D terms are three, and the lambda n term in the continuity equation are completely arbitrary, okay? The problem in this case is that all these coefficients are nonlinear term, but the infrared scaling is precisely controlled by nonlinear terms. Now, um, on top of that, from the original paper of 1995 of Tonner 2, the determination of the fixed point has entered into trouble. So the first attempt to derive this exponent was in 1995 by Tonner 2, and they derived some critical exponents which were significantly different from the Vixet model. Later, they found that they didn't include in their analysis a nonlinear term which were important. So at the very end, even just up to 2 years ago, we were in a situation where it was not clear if the Tonner 2 equation was indeed an effective equation for the Vixet model or not, and most of all, what were the scaling, the exact scaling of a fixed point, even in the Tonner 2 system. Okay. So it was there that we came using our technique to try to solve this problem, and our solution. So basically at the same time as us, Châtet and Solon came with a complementary solution to our the same conclusion of us. Okay. Now I will explain what we did and comment briefly about what Châtet and Solon did. So basically, what we said, since we were expert in deriving hydro from a generating functional, and we were also expert in system that hydro system that do not respect Galilean boost symmetry. We use this technique to reproduce the Tonner 2 equation. Okay. So what we did was to say, first, contrary to what people usually do, since you are breaking boost, the velocity, as you do typically in a boost agnostic formalism of hydrodynamics, must enter into your equation of state. So it must enter into your equilibrium generating functional. On top of that, unlike Galilean fluid, where momentum is directly related to velocity through the mass, in a boost agnostic case, this is not typically the case. So you have a generic density, which is now a function of the density at equilibrium and of the velocity at equilibrium, your V0, your alpha over beta in the Mexican egg description. Okay. So if you do that, and you start just deriving your equation of motion, you can basically eliminate V in favor of momenta, and you can use your equation of state, just making it very simple, not really entering into details, to fix some of the coefficients that appears in the Turner 2 equation. So basically, all the coefficients that are ideal, comes from ideal hydrodynamics, are just described in terms of thermodynamic derivatives of your equilibrium function, okay? And at the moment, no microscopic mold is assumed at this stage. So I don't have any intuition about what's the microscopic origin of my system. Okay. So if you just do that, just not including any other ingredient, what you find is that lambda 1, lambda 3, lambda 2, and lambda n are fixed just by the equation of state. The precise form of this coefficient is frame dependent typically, but the lesson is robust. So you have that instead of having the four lambda are not really independent. Uh, Now, of course, at this moment, we didn't actually add any activity into the system, so we just required that we have a system that is boost agnostic and is consistent with some thermodynamic equilibrium in which the equation of state contains the velocity v0. Of course, one should check that if you add to this framework the activity potential, so the ordering potential U and the non-thermal noise, you still have the same condition on the lambdas. And indeed, you find that from the generating functional perspective, the story is not modified by this stuff. Okay. Very good. Now, if once you have done that, so once you have performed an equilibrium analysis, you should fluctuate your equation of motion along the parallel and the longitude and perpendicular direction to v0, and analyze the system just around your equilibrium configuration, okay, as you do in the standard RG equation. So if you do that using our approach, using the thermodynamic generating functional, you find that the system has some, say, a couple of equations for the perpendicular velocity. The parallel one is massive, and we have integrated it out. Which depends on the diffusion constant, which you cannot fix in this approach. They are just specific of your system, plus some nonlinearities. These nonlinearities are controlled by phenomenological coefficients, which in the literature are typically called W and G. Now, the main point is that except the diffusive constant, all the nonlinearities in our approach are basically function of equilibrium thermodynamic data or their derivatives. So a technical question now becomes how these nonlinearities do normalize around the fixed point. And again, you can do again something similar to what Toner and 2 have done. So you set an anisotropic scaling for your system, and you perturb your system, and you generate the scaling of how these nonlinear terms must run according to the normalization group. Okay. Now the point is, if the graphs, so this perturbative correction vanish, the fixed point scale invariance just fits completely the exponent. Okay. Uh, what is our proposal? What we assumed is that since most of these nonlinear terms in the boost agnostic framework are just coefficients which depends on thermodynamics and their derivatives, they are defined just in global equilibrium. And at global equilibrium, there are no hydrodynamic fluctuation left to normalize those values. So basically, what we said is that all of the coefficients that are belongs just to ideal hydrodynamics, so that are fixed by the equation of state and your generating functional, cannot normalize under perturbative correction. Okay, so if we imposed that, that was enough to fix all of the scaling of a critical exponent of a Vix model. Basically, we just by imposing this non-renormalization condition, we were able to fix the critical exponent of a Turner 2 equation. And what we found was an equation in arbitrary dimension, because our approach was basically independent of the dimensionality, which allows us to fix this Z and chi in this way. Okay, for d equal 2, we have z equal 4 over 3, Greek z to be equal 1, and chi equal minus 1/3. Now, just to compare to what the people have done, let me say that Châtain and Solon, in a different perspective, just derived exactly the same equation as us. Okay. So if you compare to what people have done, these were the Turner 2 results corrected by some nonlinear term which were discovered in 1998. These are the numerical values for the Vixec numeric, and this is the 2D values of our work. So as you see, the agreement is surprising, okay? Just let me comment briefly on what Châtain and Solon did on a different perspective. Uh, they wrote the ordered phase Goldstone theory directly, so they assume to be in the ordered phase, and they derived the scaling just from the symmetry of a single equation for the Goldstone boson, imposing the scaling and some non-renormalizability condition. They arrived exactly to our result. So our take-home message is that the activity, so the fact that your system is active, doesn't mean that you have a huge part of a huge set of phenomenological parameters that describe your system. If you assume that your system must be still consistent with a certain notion of thermodynamic equilibrium, you must most of this arbitrariness is washed out, and you can actually find that the Turner 2 equation are indeed very close to the Vixec point, Vixec model fixed point. Okay. So basically, that was my presentation. So I thanks the organizer for letting me speak. And if you have questions, please ask.
Questions?
So I might have a naive one. So in the end, you said that you derive, what was the conclusion about the noise? That it shouldn't be Gaussian, or it's still Gaussian?
No. The noise is Gaussian. This is just as in the Vixec model. I'm just saying that it doesn't spoil if you add the noise, you don't spoil the fact that the lambdas are mostly fixed by thermodynamic derivatives.
Okay, sorry.
I also have a question. I think I missed the link between the first part of the talk where you explained that you wanted to have spontaneous symmetry breaking so that the velocity would take a fixed value and fixed orientation. But then you use boost agnostic fluid hydrodynamics to describe the system. And so there's no spontaneous symmetry breaking anymore.
No. I mean, okay, the first part was just an historical introduction of why the Turner and 2 invented their model, for the reason why. Now, this Turner 2 equation is just used as the most common way to have an hydrodynamic description of of an active particle. An active system, and what they do is basically a boost agnostic hydrodynamic theory, because they don't have boost, and they add these potential, so that you can do also in a boost agnostic framework. You start with your generating function, which tells you the ideal hydrodynamic part, and you have dissipative term, and this potential belongs to the dissipative part. Of course, you cannot fix that, but it's just what we said is that most of the ideal term, just using boost agnostic generating function, are fixed by the thermodynamic condition. That's the point.
So conceptually, you disagree with them.
With Turner and 2, yes.
And also with Sauton and Chalet, because Châtain and Solon, because they apparently formulate the theory in terms of spontaneous symmetry breaking, and you're saying that you don't need to do that.
No, I mean, you do, wait.
And you're telling me that in your description, there's no spontaneous symmetry breaking. And in theirs, there is.
No, wait. No, I'm not telling you that. I'm telling you that in order to have, so the lambdas are fixed just by thermodynamics. Of course, there are other nonlinear terms in which you must have the activity. So the point is that you need a V0 to be picked somehow to do all this analysis. So you need a certain V to be non-zero. So you want a mechanism to select a velocity. So of course in Boustanotis agnostic hydro you don't have typically. So you say that the velocity is fixed by some mechanism that you typically don't consider. If you want to be more specific, you add this Mexican net and you fix the velocity to be V0. Okay, so that's the point.
Like his theory is describing just the Goldstone boson, not how it appears.
Yes.
You have a theory for the phonons.
Sorry, I didn't get that.
Like his theory is just about the Goldstone boson, not of how the Goldstone boson was created.
No, I'm still confused. If it was a hydrodynamic theory with spontaneous symmetry breaking, then there should be an explicit massless degree of freedom that corresponds to the Goldstone, and there isn't here. It's a fluid hydro.
It's fluid hydro, but with a certain V0. Okay.
Fine.
What I'm saying, okay, the point is that to fix the scaling of your the relevant scaling, you don't need you don't need the massless degrees of freedom. That's true.
Okay, thanks.
Okay.
If there are no more questions, then let's thank Andrea again.
Ciao, thanks.
Thank you.